Hello, how's everyone? Well, I kind of see everybody. I did. Oh, okay, one person is okay. Everybody is a maybe. All right. Well, happy Monday. Oh, two people are okay. All right. Climbing up. All right. So I hope you had a good weekend. It is pretty outside, but here we are locked inside in our virtual world. I'm going to start the presentation and start sharing. Today, we are going to work on visualization. Let me just open up. Did anybody have any issues with ParaView? I'm going to take that as no issues installing. It typically really does fly out of the box. I haven't really seen problems with ParaView. The problems that do arise come from data being too big, and that can shut down your computer real quick. I actually, the other day, had ParaView open, and I left some data in there that I was working with, and it was 500 cube. And 500 cube is a sizable in any kind of image processing, and I think I was creating Surface, which would what we're going to do today, and I left it kind of open, and then within an hour or two, a lot of things in my computer started kind of failing or struggling, to say the least. And I didn't realize, oh, I have actually a pretty intensive process in the background that is taking up some memory. So be mindful of large data sets and opening up, specifically producing surfaces with them. So just as a quick review, we have mentioned marching cubes algorithm that basically creates or places surface in a volumetric image, but of course this can be done in 2D as well. And in 2D, we typically look at contours as separating different phases in the image. So behind me, this is actually the reason why I'm using this background today. Behind me, you can see the black is, if you remember, this is the oil blob in a Ketten limestone. So in this, if I was doing contouring in 2D in this particular cross section, I was going, I can put interface in between, for instance, this oil blob and everything else, or possibly between this Ketten limestone and everything else. In 3D, that becomes a surface. So the classical algorithm that puts together this surface tries, for instance, to separate and place triangles, a set of triangles in every little cube of neighboring voxels in an image that separates those algorithms, that separates those phases. And then once I do that, I assemble all of those triangles in one big large surface that is a triangulated surface. So all of the surfaces that you are actually looking at digitally are actually sets of triangles. They might appear smoother or not, or less smooth, depending on how they were done, but ultimately those are triangulated surfaces. That's how we represent surfaces, basically as a set of triangles. Any kind of files that are working with those are also doing the same. They're typically recording the set of vertices for a triangle, as well as set of triangles that are referring to those vertices. So that's something to keep in mind. Now, let's look at one example. So for instance, let's see that I'm in 3 dimensions and I have 4 neighboring voxels. I'm looking at these corners as center of voxels. So I cannot, of course, show all of the voxels because then I won't see anything. So if I have this, and let's say that only one corner is phase 1, everything else is phase 0. So if I were placing a surface that separates phase 1 from the rest, okay, then I would basically place this one triangle. And I can place this triangle a little closer to this corner or a little further away. That's sometimes scales with the values that I have chosen, as well as this what's called an isosurface. So for instance, in this particular example, my isosurface, this would be around 0.3 or no, 0.7. Let's say that this is a 0, this is a 1, this is approximately at 0.7. So this would be isosurface or contour 0.7, separating this one triangle, separating this phase from the rest. I essentially have multiple configurations, but it really comes down to when I account for rotation and things being equivalent just by rotated, but possibly rotated and flipped over. I really have about 15 unique configurations where I have a set of in 15 possibilities, and I can really set up a lookup table and assemble this surface. So quick quiz for you. Draw this on a paper. So on a paper, or if you have a chance to do this digitally with a mouse, take a snapshot of this and draw on it, or otherwise place triangles that separate red voxels from the black voxels. And the same thing over here. In the meantime, I'm going to see my. Uh-oh. Oh. So again, draw some triangles that somehow separate red from black. Red phase from black phase. Let me know when you have had a chance to think through. Is anybody ready to tackle this first one?
I think I have the first one.
Okay.
Or just share my screen.
What is the challenge? What do you want? I want to place surface that's episode. If this red dots and blue dots are two different phases in an image, and I'm showing their center of voxels. So I have red phase voxels and black phase voxels. How do I draw triangles in this cube, the first one? Let's say that I'm looking at this one. How do I draw triangles that separate those two phases? These are voxel centers.
Yeah, it's basically like a plane of 4 triangles anywhere.
Right.
Like
so the
between
yes.
black
So
and
the procedure here is that, okay, let's say that this is 0 and this is 1. Then, and I want to draw a plane at 0.5. Then at 0.5 in between, so on the line between two different phases, I'm going to draw a vertex. So this surface has to go through these 4 points, right? And now I have a choice of how do I put triangles in those points. Typically, surfaces are triangulated. And one choice is this. This is triangle 1, and this is triangle number 2. Okay. So in this case, this is my plane, and this plane separates these two. How about, and my other choice is just switching the orientation of triangles. So basically I would draw, if everybody sees, I would draw a line here and have basically a symmetric version of this. That's a matter of choice, okay? Now, how about this other one? This one. And hint, I would proceed the same. So basically if I have a line between two, so if this is a pixel of phase 1 and this is a 0, then 0.5 has to strike in between. So I'm going to place a vertex right there. And then there has to be another vertex here. This one in the back does not have a vertex because both of these voxels, it's a line between voxels of the same phase, but there has to be something here, 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 and here. So basically something like this. Oh, excuse this random drawing by my. And then again, I have a choice, so I'm going to do this. Ah! Does everybody see this? So this is my plane, but basically it's 4 triangles. And this is 2 triangles. So I march through cubes like this and basically assemble the surface. Any questions? Okay. All right, well, here's my solution. All right, so let's do an exercise. And first exercise will be in image J. And the second exercise will be in ParaView. Word of warning, image J was not created for surfaces, or actually initially it wasn't really created for 3-dimensional data. So while image J is actually great at this point, it is very good at manipulating stacks that create volumetric images. They're not necessary. It's not necessarily ideal for the surface generation and three-dimensional manipulation. It's not actually very memory effective. Now that depends on the plugin and how plugin has been put together. Nevertheless, we can certain smaller volumes can be effectively imaged within ImageJ or Fiji. I still prefer ImageJ and Fiji for basic manipulation of images and quick insight into data sets, even when they're three-dimensional, and basically any kind of resizing and physical manipulation of those. It's also pretty good about recognizing a range of data types, which is always very useful. Let me just silence my phone quickly. Okay, or just. Okay. Now, for more effective visualization, one needs to go to a different software, and there is a range of options. ParaView is one of them. There is a couple of others, but ParaView is one of the most mighty right now. It's also useful because it can actually do or process information that comes from parallel simulation. That is actually ParaView. That para part comes from parallel simulation, and it is open source. Okay, so those are just initial comments about visualization. But again, visualization, especially of surfaces, is intense. So let's actually load the sphere datasets that we already worked with. That is segmented already. So open up. And it was import raw. I think it was in, no, it's not in surfaces. Was that segmentation exercise or medial axis? No, I don't know anymore. There was a single sphere. Maybe I need to read my slides. I thought that I remember. Topology, of course. Oh yeah, it's right there. Sphere. So we can just breathe in the sphere. I think it's 192. Where did my sphere go? Something's off here. Let me do it again. Ah, that's better. So if you remember, as the sphere. So how do I get surfaces? Let me actually just quickly go to the basics. So there is two fundamental options for surface visualization in ImageJ. They're BoneJ plugin that we already used. There's ISO surface, and there's also image a 3D viewer where you can display as surface or as volume render. I'm just going to quickly look at this image 3D viewer because there are two different concepts that you can use there. They're important to mention. So if I go to 3D viewer, we can run. Okay. So this is the image. You have to click on the image to actually to start 3D viewer. You can display as volume, ortho slice, surface, and multi-ortho slices. Now we have already done orthogonal slices. I'm not necessarily going to do that here. It can be done through 3D viewer, or it can be done through a different the stack. There's another option for orthogonal slices that we looked at already at the beginning of the course. What this volume does is in all of these visualizations, you're looking for the threshold. That's precisely this boundary that you're trying to visualize. But that typically is relevant to surfaces. Now in volumes, what it's going to do is basically stack, it's going to sort of stack little boxes and make them semi-transparent, and that's going to basically give the appearance of three-dimensional visualizations. Now, typically, if you are thresholding the data, you also have to know what that data is. Okay, so basically, in this particular case, we have a segmentation that is between 0, which is black, and 255. So threshold is basically anything in between. So I'm just going to immediately, as a default, that value put it as 127, which is right in between. And I'm not going to resample. I'm just going to put resampling factor 1 for now. Okay. So if I place OK, you will see this stacks or three-dimensional visualization of the surface. You can now, of course, play with things. So let's do actually right here. Where does it go to? I'm gonna put surface. I'm gonna now play with colors. Let's put red. One. Okay. So you can play with colors. And I'm gonna now resample. I'm gonna put that in C. Yeah. Okay. And you will see that resampling gives a smoother surface. That appearance is actually much better. And the smoothing actually resulted in subsampling, or resampling basically means, when I say resample with a factor of 2, that means that every 2 by 2 by 2 set of voxels will be replaced by 1 voxel. So you're actually downsampling or upscaling in a sense. And that produces smoother result because there's typically some sort of either binary interpolation that is going on, that right near the interface where this matters, it's going to smooth the values a little, and then your threshold will appear smoother as well. Let's try to push this once again, just to see even smoother. I'll do 4. And I'm gonna do color. Now I'm gonna do magenta or blue. Okay, so you can see even slightly smoother version. It also appears faster, so resampling will reduce the size of your image. So if you can't produce the surface initially, or it's taking way too long for a large set, then resampling is a good idea. But that's essentially, you have essentially reduced the size of the image. Did everybody get this?
Yes, but I have a quick question. In this specific case that we have this sphere, is the volume of the surface the same for the visualization point of view?
From the visualization is just the visualization. Now, if I were to create surface area from these 3 different areas, there will be an influence on the resurface area, on the area, because you're drawing slightly different triangles, and you're losing a little bit of detail. Now, that shouldn't be a large influence, but it's there. So you can actually do this. Let's see, just a moment. Let me see if image viewer does it. Normally, I would go to BoneJ particle analyzer for surface area. Let me see if this is a good question, whether 3D viewer has anything like that. No, I don't think it's, no, cancel, okay. Let's go to BoneJ. There's a particle analyzer. And apparently it actually has immediately surface area. Let's try. Oh. So this is done in pixels squared. It did not tell me any factors. So what I'm trying to figure out where to put resampling details for BoneJ to calculate. I think I know. BoneJ particle analyzer.
Yes, you can. You have the
Yeah,
resampling there.
yes. So that's going to affect. Let's actually do that. That's actually part of the suggestions on the slide to do that. So let's do surface resampling of 0. Oh, 1, excuse me. To me, it's like no surface resampling means I'm putting in 0, but the factor is 1. So keep the same, and I don't want any of this. All I want is surface area, and volume is fine. Okay. And I can show surfaces, but I don't need anything else. Okay, all right. So this is a similar result. And this is the surface area. Now let's resample. I'm gonna do 4 just for kicks. So you can see the smoother result. And now the number, it was 21,000, now it's 20,000. And it actually flashed the time it took, so it takes also less time, of course. Let's just do one more. So this was 20,000 to 230. Let's go to one more. Let's do 8. So a little less. So technically with the resampling, there's a little bit of smoothing that actually removes the staircase effect. And that reduces the surface area ever so slightly. Did everybody get a chance?
Eventually,
Question?
if you keep going up with the like resampling, like the triangles keep getting bigger, eventually the sphere becomes a cube, right? Like there is a limit to how much
Right.
it's smooth.
Right. It's still a sphere in some world.
Topologically speaking.
Topologically, it's all the same. There we go. We learned something. Score. So part of it is like that you do have to be careful because you are removing details. And that can be okay for some applications and not for the others. For sure, it's going to look smoother and look better, right? But that, that can be problematic. And the data that is more robust in that sense is essentially what would be distance function. Would probably be less prone. First, it would be less prone to the staircase effect, right? But the distance function would actually create a smoother edges because with distance function, so if I create distance, let's actually try that. If I create distance data out of this, the only problem is it's going to ask me to create, well, let's give it a shot. So let's me try to process and do signed distance transform. So this is my signed distance transform of the sphere. I am negative inside the sphere. Oh, wait, I'm negative everywhere? Let's see. So I am, yes, I'm positive inside the sphere and I cross over to negative values as I'm going. The only problem is that in this, for this, if I try to work Bone J and or 3D viewer, let's try 3D viewer of this. So technically, the problem with analyzing this is BoneJ is not going to want to analyze 3D data. We can try, but or plot the surface. Yeah, it requires non-smooth data, so that's the problem. Let's try a 3D viewer if it's going to want to work with that. And let's try surface, and let's try to put the surface at the 0 without resampling. Yeah, okay. Conversion is going to mess it up. Yes, it did mess it up. Okay, I didn't get a surface, so something got messed up. So part of the problem is that this data, the Euclidean distance, it's smoother. It has smoother values, so it's better for visualization. We can probably actually take this to ParaView, and we can do that later when we start working with ParaView. If I convert the data to 8-bit, I might lose it. Let's see what I get by the immediate type conversion to 8-bit. I'm getting it. So now it's hard to know where did this conversion send my interface. So you can see the issues in processes. So I will get the data that is smoother because of the Euclidean distance. However, Euclidean distance is through 32-bit data and floating point data. And I go from negative to positive values. If I automatically convert this to 8-bit, it's going to do it. And now I have actually all of the values between 0 and 255. But the problem is that I lost my information on where is actually my interface. I don't know that it's at 127. I can try. Let's try. But it might not precisely be at 127, depending on how that conversion to 8-bit happens. Let's give it a shot. So I am going to do a 3D viewer. And I'm going to work with surface. I'm going to put it at 127 and hope that it converted the way I would expect it. Let's do green, why not? And no resampling. So this is it. It's a little smoother, but not too much actually. So Euclidean distance gives me a little smoother result than just original segmented image. But I did create Euclidean distance from segmented image. So no matter what, you're going to have some staircase effect if you're doing segmented data. You can remove that staircase effect, at least visually, by some resampling, but you are actually removing some of the details, and that might be okay for visualization purposes, not so okay depending how many levels of resampling you do for surface area estimation and so forth. So those are the certain decisions that you have to work with. The best would be actually, since this, well, if this was a sphere, you can analytically create the field of values, the distance values, and that field is very smooth. Segmented data always has a little bit of staircase effect to it.
And you generate the surface with AB data that hasn't been segmented?
Yes, so here is the thing. The way yes, I have, for instance, a result of simulation level set simulation that is smooth. And those surfaces are very smooth. They're actually result of solving a partial differential equation. Therefore, by itself, those results are twice differentiable. Or the result by itself is a function that is something that is twice differentiable, and therefore those are smooth. That's the case with the result of simulation. In terms of X-ray data is smooth, or rather you have tomographic values. But the problem is that you have to filter it. So yes, I would do that, but with heavily filtered data. Does that answer your question?
Yes, thank you.
The problem is noise, because that noise will be reflected in surfaces, and part of the segmentation process is removing the noise that is inherent in X-ray data. So technically, once I go through the segmentation, even though I might have a little bit of a staircase effect on the surface visualization, that can be removed by bilinear interpolation just near that interface if you really don't like that non-smooth data. But I would actually work with segmented data, because hopefully you have thought through that segmentation and filtering and removal of the noise. And once you've done that work, you kind of don't want to go back. Neither is perfect, but you don't want to go back, because in cases where the grayscale data was so great and smooth to begin with, then sure, but that's rarely the case for X-ray, especially of natural materials. So I tend to work with segmented data and visualize those. And if you need some smoothing for this beauty, there's things you can dress it up by a little bit of bilinear interpolation, or bicubic possibly near that interface, and that will give you smooth fitting. But that's dressing things up. And visuals are important. I'm not saying just don't. If you fit this into something smoother, that doesn't mean necessarily that your surface area estimate is more precise. That's the reality. Okay. So those are that is the surface, the basic surface understood through the sphere. But the sphere is an important thing because we know how to describe it. So you can basically look at the differences between segmented world or the digital influence through the sphere can be appreciated through the sphere, because we know what we would expect and we see what we get. And of course, in this case, that we never did, but technically you can calculate what should this sphere be in terms of its radius. What should the surface area actually be? Okay. So something to understand. You can actually export these surfaces and then just visualize them as surfaces, as so-called STL file. It's short for stereolithography. And again, just that stereolithography file is just really a set of triangles. So it can be visualized, it can be quantified. Some of those triangle areas is my surface area, and that's how Bone J came up with it anyway. And then you can also do simulation using it. So this type of manipulation is important for simulation as well. Finite element software can basically create finite element method volume, or finite volume method as well, from these triangulated surfaces, and that's actually the format it requires as input. If any of you have mechanical engineering background, that's what you often do in AutoCAD software. You will create from, geometrical shapes of the machinery and so forth. You can create STL surfaces again, and they're the input for finite element method. And you can also do 3D printing. And this course at this time would actually have homework that would be, oh my, did I publish homework? I did type it in. Did it actually get to you? Did it get correctly?
No.
No? Oh my, okay, well, you're getting it today. My bad. It was supposed to be done on Wednesday. Look at me. Homework, let me. But at this time, I would actually ask you to go and create a surface for 3D printing. Unfortunately, we don't have access to campus and the Maker Studio in ER building, so that exercise can be left for when the campus opens. But again, this little sphere that I just showed you, we could create the STL file that you said you can go and 3D print. Okay. Now, in terms of visualization software, we have just explored what Fiji or ImageJ has to offer. MATLAB by MathWorks is very good, and its visualization in itself is high-end. However, it's not good for large data sets, and often we deal with very large data sets. But don't forget MATLAB Central Exchange. It might actually have a solution to whatever visualization problem you're running into, even though you're on a very small scale. Also, something to remember is that MATLAB in itself has, I remember seeing like a 300-pager PDF, not the course, but the tutorial on visualization. So it's a very good place to start, and it has a lot of videos online where you can learn the basics of visualization in an environment that is pretty easy to comprehend. So that's something to have in mind. ParaView is also great in terms of the tutorials, and then Visit and Mayavi. So ParaView is open source. However, it actually has a company behind it. So that company has found a model where they're saying, okay, we're going to give you the fundamental software for free. There's a lot of tutorials online that are done by both Kitver, the company, and other people. I think they want to charge you for an actual PDF of the user, some PDF of the actual. So they charge you for the actual written tutorials. But that said, there's a lot of knowledge of ParaView online where people have posted how-tos on YouTube that you can access. So they give you certain fundamental things for free, but they still charge, and they charge other companies if they have visualization projects. So that's their model of how they make money and still remain, still give things as open source. Visit is an open source. It's developed for visualization of parallel simulation by Lawrence Livermore National Lab. It's also pretty powerful. However, it's a little harder to start in, much harder in my opinion compared to ParaView. And then Mayavi, it's original open source visualizer, and it was recently purchased and revived by a company called InThought, which is an Austin company. And that company is still now providing it as an open source, and also has online tutorials. So that's probably it's probably going to strengthen even further. From what I see online, it actually has pretty crisp and beautiful visualizations. So these are the software that I would go to. We are going to exemplify ParaView. And something that is important to think about is Python, and Python is becoming sort of a uniform glue of different types of software. In itself, let me use the word, it sucks at 3D visualization. In itself, Python is not done for visualization. It's Matplotlib for 2D is good. It has a lot of extensions that does very powerful visualization that are that is visualization effectively in 2 dimensions, but for 3D is not good. What's good about Python though is that ParaView actually has Python shell, and you can interact with ParaView from Python, and the same is true for MayaV. So you can integrate a more powerful visualizer such as ParaView and MayaV, which is made for visualization. Python was not made for visualization inside inside your Python script. So that part is definitely powerful. There's the software list actually does go on, but I would say that these are the major ones that are very well documented in the on the internet right now. There's also Drishti. Dragonfly is relatively new. There's a company behind it. It's my understanding that Dragonfly is actually free for academic use, but not necessarily for private companies' use. Again, but the ones that I mentioned are currently well documented online. And MATLAB is not free, but it's free to you as a UT student, so that's there. Okay, now ImageJ and Fiji I have already commented on. One thing that you have to also understand that the hardware issues, you're going to likely hit some hardware issues in terms of memory. Datasets can take a lot of memory once you're producing a surface, especially in porous media, especially in porous media. If you have a porous material with intricate geometry, that intricate geometry will place these interfaces in way too many locations. So that's a lot of triangles if you think about it through the marching cube as the algorithm. So the more complex the interface, the more memory it takes. So it's also harder to rotate that geometry and work with it. That little sphere that I was rotating was easy to work with. So if you're looking for a personal computer that does visualization rather well, then pay attention to the video card. That video card has, I would say, a minimum of 2 GB memory, but even more. Or look for gaming machines. So gaming machines are intense in terms of visualization, so those will be geared towards that. The Texas Advanced Computing Center, it basically provides an entire portal. I used it in one of their workshops. I don't use it interactively, but essentially you can interact with their parallel visualization machines. So there's Stampede 2, Frontera, Maverick is getting out of commission, but those machines you can actually run visualization that is much more intense than any single machine. And you can interact with those visualizations through, for instance, Python or any kind of online. So basically you can interact with them through the website. And most of the time, the way visualization works in parallel machines is that you're gonna view the whatever you're visualizing on a parallel machine, you're actually viewing through a web browser or remote desktop environment. Okay. So, and consequently, Texas Advanced Computing Center provides sort of an entire portal, not just entire portal, but also a set of, you can look for their online courses. They have quite a bit of recorded courses, but they also throughout summer typically have courses that you can take for an afternoon, 2 afternoons, and so forth in visualization in itself. Okay, so let's give it a try. I'm actually gonna do visualization of this blob that is behind me just for kicks. So I'm gonna close up my ImageJ. I can come back to this if I want to. And what I'd like you is to open ParaView. Whoops. I'm actually going to delete all of these and start from scratch. Okay. So you can edit your preferences. My personal preference is to have white background, especially if I'm producing papers. Don't go in with dark blue or anything like that. It's not good for printing. It's not good for actually human eyes. So PowerView opens up, and first things first, you actually have to open a file. What I'm going to open is the file, the same file that you worked on in homework that is behind me. I have actually downloaded it in what you will see in the data that I shared at some point. There's PowerView visualization, but you can simply go to the website and download it. Let me show you where. So if you go to DigitalRocks portal, projects 125, and then analysis data, it's a project 125. And then the segmented oil blob that we worked for homework. So we're gonna try to basically produce this image that is shown on their website. So this is the data set. And again, the same comment that I made at the beginning, I'm actually going to the segmented data as a source of my visualization, because now that I got segmented, I kind of trust that that's where it's at. But you could basically use this filtered data. This is pretty smooth, so it would work rather well, most likely, for visualization purposes. Javier, that goes to your original question. Did everybody download it? So this data is a raw format, so I have to import it. And the way you import, so if you remember in ImageJ, we had to go through import. PowerView does everything through open. So I opened, and basically it's a data that is 365 by 255 by, it's actually 225. And you open data with image reader. And here you actually, it hasn't opened it yet. For image readers or any kind of binary data, you actually have to tell it all of these details, just like we have to tell ImageJ. So first thing, image type is 8-bit, short is 16 bits. So this list is slightly different than it is, or uses slightly different naming compared to ImageJ, and that's just the reality of how these things work. Character and unsigned character are 8-bit data. Unsigned character is 0 to 255. Just character is minus 127 to 128. So we're going to choose unsigned character because this data is 1, 2, and 3 actually. So unsigned character, whether it's big endian or small endian, doesn't matter for 8-bit data, but since it says little endian here, I'm going to comply. Data origin is at 000, data spacing is 1 in every direction, and I only have one scalar component in the file. This is to understand, I might have 3. This might be a vector field, right? But this is not a vector field, this is a scalar field. Okay, now data extent. So if I'm starting from 000, and I have width of 365, then my extent is from 0 to 364. If I'm having 2 255 in Y direction, then I'm going to 254, 0 to 254. And if I'm going from slices are 0 to 224. So this numbering starts from 0. And for now, I can just hit apply. See, nothing happens actually. Something actually did happen, and my background is white, but so is the boundary volume boundaries. You might see them as white on your part view. I haven't really visualized anything. I just read the data. You can see information, however, information shows up, and you can see that there are unsigned characters and data range is 1 to 3. That's good. So I know actually my data range should be 1 to 3. So you actually know that you've read incorrect data. Here in information, you also see the memory number points and so forth. Okay. Now we're actually going to do, so there is a contour. Whatever PowerView does to your data, it calls it filter. So you kind of stack different filters. And you have to be careful to, just like in ImageJ, you have to click on what do you want to work on. Now here we have only one data, so of course that's the only thing I want to work on. But in filters, you can actually do all kinds of, I could, for instance, histogram all of these values, and I'm gonna get 1, 2s, and 3s. Let's give it a shot. And if I say apply, you will actually see 1, 2, and 3. Cool. Okay. So any type of data you can histogram, and that's called a filter. Now I'm gonna remove the, so if I click on it, I can view it, or if I unclick it, I don't view it. I'm actually gonna go and is everybody okay where to find the histogram? I'm gonna delete it for now. That's not what I'm here to look at. Okay. So I want the contour. Contour is a filter, and you can find it on this filter list, but there is also a shortcut for it. So I'm gonna use the shortcut. I'm gonna add a contour, and you can contour or as a surface, same thing. So this first contour, my oil is 1, my brine is 2, and my rock is 3. So first I want to place a rock pore space surface. So whatever is in the pore space, oil or brine, is 1 and 2, and rock is 3. So my pore space, rock space interface is technically in between. It's 2.5 will work as an interface between the two. Okay, so I'm going to modify this. You click on this data and type in 2.5. And just hit apply. So this has showed up. I'm guessing I have some red values here. It tells me how it shows my colors. You can change the colors, but this is the interface between the two. What I'm going to do is I'm going to change, there's opacity. This is a great little tool right here. I'm going to change it to a small value, and then I'm going to see a see-through surface. And I'm rotating it with my mouse. Did everybody get here? Gonna wait for you a little bit. Okay. May I proceed? Did everybody get here? Yes or no? Should I go? There's a chat. You're seeing the whole blob. You have, you did not plot 2.5 surface. This contour should be 2.5. Let me add a blob and see whether that solves the problem. So I'm gonna click back on the kitten. I'm gonna add one more contour. It's gonna be called contour 2. And blob oil is 1. Brine and rock are 2 and 3, so larger than 1. 1.2 will separate oil blob from everything else. I'm gonna hit apply. Now I see a blob inside. And I can rotate it all. So again, my contour 1 is the contour at 2.5. I have to look at the data. And that's just a little bit below rock, which is 3. And it's above oil and brine values, which are 1 and 2. So that will work as an interface between whatever is in pore space and rock. If my values are not stacked so that I can easily visualize it in that way, then I have to manipulate them a little. Okay, so did everybody get what I'm seeing? Or you could possibly have different colors. Colors don't matter. It's a personal choice. You can manipulate colors. That's the easiest thing after actually you get the. So you can also click on things and then they appear and disappear. Now you see me, now you don't. So this is the little eyes right here. And you have to be careful, like you don't go, this contour is a different object. It's a triangulated surface. So you cannot now take a contour of the contour. That's not gonna work. Did everybody get this? Or do you have any questions? Do you have any problems? We can edit the color here. Just a moment. So you can put the range here, different range of colors. You can edit the color legend. That's not the color scheme. Should be here. You can play with those. That's the minimum trouble of them all, as long as you can see. For instance, change the preset color map. So I have changed the blob to a slightly different color map. That's too dark. X-ray. Lighter colors are better visibility on screen anyway. Too dark and you can't see surface details. So one comment that's something that I did not, I actually did have apparently trace enabled, but there is tools, start trace. This is equivalent of record in ImageJ. So let me see. My recording is running somewhere. I just have to see where's that window open. Oh. Well, if I probably stop it, I'm gonna find. So I started a trace. Actually, when I started playing with this, and this can now, when you start the trace and after you stop it, so you can see actually that this is a paraview. So there is importing paraview.simple as a paraview set or little library that you can import in Python. So this is a Python trace. And then after that, basically there's reading, so it creates and reads image from a specific location on my computer and so forth. So this is a trace of everything that I've done. And I actually opened this just before the class and then again, once again in class. And you can edit this or save the pieces that you like. So for instance, there's contour to display. You can see here. So everything that I was working on is saved. I can actually save that as a macro. If you save it as a macro, it's going to show up on the list of macros here. So I actually had a visualization of the sphere packing as a macro that you can then run. Okay. Let's see actually if this one will run. I don't think I moved the data, so. So this is a visualization of a sphere packing that takes a little longer, but that basically repeated everything that I was doing. And that doesn't make sense now because I didn't delete everything else, but we'll see actually. Okay, it came up with it, okay. So this is a visualization that I saved the other day when I was just trying to plot it, okay. And it has showed up. And it's a little more difficult to manipulate. It's also overlapping both of them, which, well, is not the neatest of them thing, but you can add things. And this visualize sphere packing is simply something that I saved from the previously done work, so I can just reopen it. And that's very useful when, especially when it takes a moment to make selections that you like. There's also a Python shell. For me, it's enabled down here, but that might not, you might need to go to view to actually enable a Python shell. Okay, so you can also manipulate data from Python shell. So that's the scripting that is available for manipulation. Okay, so I'm going to stop here. You can dress this up and down in multiple ways. You can also just use ParaView, what I call as a clickable. It doesn't have to be scripted, but scripting things that you find as a good workflows is definitely a good idea. So you just, again, you start the trace and you save it either as a Python file or as a macro. And if you save it as a macro, it's going to become sort of available macro for you. It's going to be saved somewhere in your local ParaView folder. Questions? Okay, I hope you have enjoyed. I'm going to delete this before it locks my computer for having too many things. I hope you enjoyed the visualization part, and I hope you will use it. You can visualize any type of data. This is not just DigitalRock Better Physics. This is visualization of any 2D or 3D fields. Okay. All right. I see you on Wednesday.